You were introduced to bias-variance trade-off before. In this lecture, we want to deep dive into bias-variance trade-off and explore it a bit further. Bias and variance are two key concepts in machine learning that describe the types of errors a model may encounter during the training process. The bias is the inability of a machine learning method, such as a linear regression, to capture the true relationship and patterns of data in a dataset. To calculate bias, we can use mean squared error, for example. A high bias model can be compared to a movie recommendation system that always suggests popular movies from the same genre regardless of the user's specific tastes and preferences. For example, imagine you watch a movie in Netflix and you expect that Netflix suggests you more movies like that, but you always get the most popular movies, or you always get recommended like action movies. That is bias because the model that is used in the movie recommendation system has failed to capture your preferences. What is a variance? High variance model predicts almost all target values correctly with the training set, but performs poorly with new and unseen data, such as test set or validation set. In our movie recommendation system, the recommendation system overfits to a user's current preferences, focusing too much on the individual habits of the user. YouTube is a bit like that. As soon as you watch something on YouTube, for example, say a documentary about World War II, you keep getting recommendations about World War II. So let's see bias-variance trade-off on a diagram. So imagine that those blue lines are our training set. So the left side is showing the bias, the right side is showing the variance. So if we use a linear function that draws that red line, you will see that with the training set or those blue lines, the loss is quite big. And no matter how we move that red line, there will be always some loss because the straight line can never fit a curvy line. So no matter how you move it up or down or just change the angle, it never fits the curved line. So you will have some loss of data. And that is bias because we can never capture all the values and relationships in that data. The relationship in that data is the curve, and we can never capture that curve. Now imagine that at the right side, instead of using a straight line or a linear function, we use a function that connects all the dots in the training set together. So with the training set, the loss is zero because we have captured all the values, all the target values. Now let's put the red dots or the test set on the diagram. You will see that again with the straight line, there is some loss. However, the loss of the test set is very similar to the loss of training set. However, at the right side, the loss with the test set is much bigger than the loss of training set. And that is variance because our function overfits the training set. It perfectly goes through all the circles in the training set. But then when we give it a different set, which is quite unknown to the model, it just has a big loss in there. And that is variance. So variance is the deviation between the average prediction values and the predicted values. We can see that in the diagram at the left side of the screen. So if that thick gray line is the true function and we have 3 training sets, you will see that those different shapes, they are quite different. For example, the blue ones almost fit the curve. However, the gray circle ones are quite off. And also the gray rectangles are quite off as well, and that is showing the variance, the high variance. Because the squiggly line that we draw and we connected all the training dots together fits the training set really well, but not the testing set, we say that squiggly line is overfit. So how do we optimize the bias and variance? In this diagram, you will see the model complexity on the x-axis and the errors in the y-axis. At the very left side of the diagram, when the complexity is very low and the model is too simple, we get so many errors because the model is too simple and it doesn't capture the relationships existing in the data. As the model becomes complex, the number of errors reduces and it goes down. However, from a specific point, Again, it starts going up. The number of errors starts going up again. That specific point is the ideal data selection. That is where your bias is minimum and is your variance is minimum. However, it normally can never become zero. You will always have some error. And that green line shows your error. You can never get rid of that error. And in formulations, we normally show that error as an epsilon. Three commonly used methods for finding the sweet spot between simple and complicated models are regularization, boosting, and bagging. In the next section, we will explore bagging a little bit more.